Okay, thank you, everyone. I think we're going to get started. I'm Therese Jones. I'm the Senior Director of Policy at the Satellite Industry Association. We're an trade association representing about 50 different satellite companies. And I want to thank Mariba and Diane for putting on such a wonderful conference and ending this conference on what I think is a really great topic, and with many different perspectives on AI and cloud computing. So for this panel, you'll hear from a wide variety of experts from law and policy to technical experts. And hopefully this will be a good note to end this very multidisciplinary conference on. So first up, we are honored to have a judge kick us off on this panel. So the Honorable Judge John McClellan Marshall. He's a senior judge of the 14th Judicial District of Texas and has served as judge presiding of the Municipal Court of Munster, Texas, and many other positions. He is a prize-winning author specializing in procedural law and ethics. He has also served as a historian on the Apollo program and a technical instructor on the Skylab program at Kennedy Space Center from 1970 to 1973. And he's going to get us kicked off thinking about ethics and AI.
Thank you very much. Now, ladies and gentlemen, before we get started, I want to ask if you have with you a pen or a pencil, a writing instrument, just kind of set it in a convenient spot next to you. We'll get back to it in a moment. And if you have an ATM card, put that next to it. I don't have a PowerPoint, I have props, okay? The topic of my paper is Machine to Major Tom, with apologies to David Bowie, for those of you who are young enough to know who David Bowie was. But at any rate, the subtitle is Cyber Ethics, which is a term I coined back in 1995 for the conference in Oslo. And cyber ethics, boiled down, is quite simply expressing the relationship between technology and conventional standards of right and wrong in the ethical world and the ability of technology to overwhelm them. We are living in that world today. For Socrates, it was much simpler. Know thyself. And that is the tension that we who deal with these topics have to consider. Right and wrong, what's right, what's wrong, highly situational, isn't it? But cyber ethics kind of gives us a feel as scientists, which you are, and as liberal artists, which I happen to be, what is going on here when we're talking about, gee, can we do these things? Now, initially, the interface that governs relationships between people would be describable as a man-man interface. And that stood in pretty good stead for several thousand years as the underpinnings and the foundation of Western society, in fact, society anywhere. Later, that began to evolve into a man-machine interface. The Industrial Revolution being an example of that. And that's when you pick up the pen. Man-machine, right? They didn't exist very much in Neanderthal times, but nonetheless. Then it becomes machine-machine to man. And that's where this comes in. Now we'll take a side trip as to what this card really is. This card is you. I don't care what they tell you the magnetic stripe on the back doesn't have. They're lying. It has everything anyone would ever want to know about you. And the moment you use it, it tells them where you are, what you bought, what you used it for, and how much it cost. check your bank statement, and it will tell you that I'm telling you the truth. This is without regard to whether or not the cell phone you have in your pocket, which I hope, by the way, is set for excitement and not to ring, that cell phone location capability isn't telling everyone where you are right now, which of course it will. Later on, machine, man evolves further, and this is where we are in the 21st century, into what can be described as transhumanism. And transhumanism, again, summarized with the Oxford Dictionary definition, simply says technology's ability to augment human nature, talents, skills, is going to help human beings evolve into something else. I want to suggest, as a thought for you, could that evolution be something that violates the first law of robotics? The robot is not supposed to injure people. That's what Isaac Asimov said. I'm sure all of you are familiar with those laws, so I don't need to keep reciting them. But transhumanism conceivably can go that far. And I'll give you some examples. We have medical progress in the technological field that has overwhelmed ethics. You have robotic surgery taking place. There's no question. Robots operate on people. Hopefully, people control the robots, but that's not strictly true. People program the robot to perform a certain task, and hopefully it will do so. We also have replacement of limbs. The experiments in England, starting in 2012, where the engineers created robotic hands that respond to the impulses from the brain of the person who has lost his hand. We can do that. That's not rocket science. It can be done. 40 years ago, when I was at the Kennedy Space Center, that would have been rocket science, but it's not now. There's another problem. Genetic engineering. As Anais Nin said, we don't see things as they are, we see them as we are. So let's consider, if we're going to genetically engineer a human being, we want that human being to be like us in the 21st century, don't we? Free from disease, free from Down syndrome, free from any sort of defect. What about an astronaut on a deep space mission? And this comes into this particular conference. We create a genetically engineered person who is going to go on a trip that may last 100 years. When he comes back to Earth, will it be the same place he left? Nope. There'll be new bugs, a new coronavirus that'll kill him or her in a matter of seconds. Some of you may remember a television program called The $6 Million Man, where a man was severely and catastrophically injured, and they literally rebuilt him technologically. That was then, this is now. Now it can be done. Almost anything dealing with the human body can be done technologically and fixed. In this process, we might be creating dinosaurs that look like human beings, because if they are perfectly attuned to the 21st century, will they be attuned to the 22nd century or the 23rd? And so, ladies and gentlemen, the cyber ethical question really comes down to the issue of not can we do these things, but should we? Thank you.
Thank you for kicking us off. on such a great topic. Next up, we have Edward Chan, who is currently a part-time master's student at the International Space University and a full-time enterprise software specialist in the San Francisco area. He has 4 years of consulting experience in business integrations, enabling operations, and supporting business initiatives for HR, finance, and IT. His interest in space grew after his participation in the SpaceX Hyperloop pod competitions in 2017, and he's actively looking for ways to contribute to the space community, particularly in integrating various SSA data platforms, and he will speak to us about that now. Edward?
Good afternoon. The sandwiches were good, right? Weren't they? So thank you, John, for kicking us off. And I want to talk about space object, data growth trend, and integration challenge today. So as the intro, I don't work in the domain of SSA or STM. So for the intent and purpose of this presentation, I'm just your tech guy working in the Bay Area, and just started looking at this since 2 months ago. So I like to read a lot, and one of my recent favorite authors is Andrew McAfee. And he said, all I'm trying to do is categorize the problem properly, because once you think about it that way, you start to understand the toolkit you can apply to it. And another quote I really like from the cloud industry. From a pure economical perspective, driving a car makes zero sense. It is one of the most expensive ways of moving a unit of mass over a unit of distance. Yet this is so expensive compared to virtually all other transportation means, public transport, trains, or even planes. Why are so many people driving cars? So think of it this way, right? Like a custom integration, point to point, that's a car. Right? If you do real time, if you do streaming, you do it by batch. In a sense, you have a bus, you have a train, right? So I started thinking about information system. I have an information system background, so I started thinking about all this data platform out there. Okay, Leo Labs, 18 Space, right? You basically have many different data platforms. So does it really make sense to have a multi-source provider then to aggregate and fusion all that out, right? Does it really make sense? What does that really mean? So the first question to answer that is like, how much data are we generating a day, right? How much data out there? How many measurements or observations are we making? And what's the volume? How should we fuse different data platforms together? Is it point-to-point? Is it custom? Is it really expensive? Imagine you hire a consultant, right? You pay him $150 an hour, or you hire a full-time employee, $80 an hour, and then he's maintaining this integration or set of integrations on a week-to-week basis. Then you're paying like easily $500,000 every year, right? So I started doing background research and kind of like a literature review, trying to understand this STM and SSA domain that's really foreign to me. And I came across this IDA paper. It's like really good. And I like how they describe like the data types. So like earlier presentation, like Slingshot did a presentation about fusion data, and also there's a presentation, the MIT Toolkit catalog talk about, like, hey, different data types, right? So I'm really interested in the orbital trajectory, the metric data. And I'm really interested in, the second level here, right? The observation, like a series of measurements. And I think that's the ideal fusion point. And then another literature out there that inspired me was this paper named Space Debris Mapping Services for Use by LEO Satellite Operators. It's written by Digital Globe and Leo Labs. As you see here, Digital Globe, they actually added a new data source to supplement their current systems. And I can talk about it later. So I started trying to figure out, okay, what kind of data out there? So I actually signed up on Leo Lab website. Thank you, Leo Labs. Thank you, Matt, if you're in the audience. So I started thinking, okay, try to aggregate and try to draw a trend to see, what's the rate of increase. So I wrote a script, very simple, just pulling instrument statistics, and then kind of put it into a database. I don't have a lot of data yet. I haven't been doing this for a long time. So as you see here, there's only 4 data points here. And I'm just kind of like, okay, based on this 4 data points, I have a slope, I have a rate of increase, and mapping it back to the first measurement date, I got a trend. So if you go on Leo Lab website today, you see they have almost, I think, 300 million measurements across the entire lifetime. And they have 3 radar sites, and they maintain a catalog of 15,000 objects. So pilot results is like, okay, I got a volume. Okay, roughly a catalog of space objects. So it doesn't seem crazy, right? If you think about being the multi-source provider, that's what you have to handle from a single platform. However, Leo Lab mentioned, they're going to install 3 extra radar sites the next 2 years or 3 years or so. So you'll see an exponential increase of data in the ecosystem probably. So it's kind of warranting a further study into this. From an operator perspective, all you're doing is really send a request to Leo Lab, right? You just want to sample a set of measurements. So that's a very simple request. That's a very simple point-to-point integration, not a lot of volumes, right? You're probably talking about kilobyte, if not megabytes size of data. So it doesn't really matter from an operator perspective, from an integration cost perspective. So this is more for like research, multi-source provider. Okay, let's say I'm an AI researcher, right? I want a large data set. I want to train my program. Then I need to curate this kind of things. Then you have to start to think about your integration architecture. So yeah, the next step is, hey, I'm an integration guy. What kind of integrations will I build, and what are their requirements? Yeah, so that's it. Thank you.
Hey, next up we have Loic Chapaz, who's going to talk to us more about data integration. He got his PhD from Purdue in 2015 in aerospace engineering. His dissertation research was dual, including trajectory analysis and mission design in multi-body regimes, and investigating the interior structure of our moon through gravity modeling for the Grail mission. Since 2016, he's served as the principal engineer at Astrolabs, which is a commercial space startup studio to incubate startup space ventures focused on products and services that will deliver rapid value growth in a broad set of commercial space business sectors. And it's a spin-off from NASA, JPL, and Caltech. With his role at Astrolabs, he's also the lead of one of Astrolabs' seed companies, Constellation Toolkit, which is a cloud framework for the design and operations of satellite constellations and space traffic management. Additionally, he's leading the effort of developing Astrolabs' Concurrent Design Center and design tools for space applications. So he's here to talk to us about Astrolabs.
Yep. All right. Well, thank you, Therese, for the introduction. And part of the introduction was actually the title of the talk, so it's going to save me a bit of time since I'm going to try to compress a lot of thoughts and ideas across a few slides, mostly because after each talk today and yesterday, I feel like I had to redo my whole slide deck to kind of incorporate new information. At the end, I decided not to, so these are the old slides, which means it's 2 days back train of thought, so not that old. But I do feel it's been a long time by now. What we're trying to do is to put together a collaborative, cloud-based framework for space traffic management. Easy enough, right? And so it echoes very well what Diane was saying this morning and was listening and nodding my head all along. Of course, we don't have all the answers today. We won't have all the answers tomorrow. We're trying to put together the frame for the puzzle and throwing some pieces in there, and hopefully we can then bring all the pieces together eventually. So we've talked briefly about that. I mean, Terry's talked for me on that behalf. Astrolabs is, to keep it short and simple, a space incubator. We focus on space technology for space applications, but also for Earth applications. And CTK, or Constellation Toolkit, is one of the ventures we're currently incubating. CTK originally is a web-based collaborative framework for the design and operations of large constellations. We've built it trying to break away from traditional design frameworks, heavy installations, heavy learning curve, hard to share between people. So this is meant to be, everybody gets on it, everybody works together from anywhere at any time. It's on my phone, I can design, I can interact with my engineers. That's just easier. And we thought this could, well, maybe not easily, but it could translate well into the STM spheres. And that's kind of what we've been working on more recently. So the platform itself, and I will maybe not admit that to an actual web developer here, is actually almost as important as the brains right now. It's because we can have great algorithms, and as engineers, we like to have our great algorithms and code, and they do wonderful things, and then we give it to people, and they don't know what to do with it. So the platform itself is entirely cloud-based. It's, it's a website somewhere, and there's a cloud backend that does all the heavy lifting, and it's built so that all the users, all the stakeholders can come together and do things. Not just your technical engineer who can go and do his thing, but your marketing, your legal, your whoever. They'll have different level of accesses. They'll have different user roles, but they'll all be able to come on and do something. It's also built for collaboration and concurrency. I guess collaboracy could work. We have chat, data sharing, Google Docs sharing, so that once you're in there, you don't need to send a PowerPoint to someone else and hoping that last week they got the other PowerPoint, and so on and so forth. The brains themselves are based on CTK itself, which is a design framework, which means you have access to this kind of deep technical simulation environment. You can model constellations of thousands of spacecraft, all the way down to the reaction wheels that goes in that spacecraft and all the behaviors that comes with it, analysis, high level, like deorbit my constellation, deploy my constellation, station keep, image downlink. All those things are kind of abstracted into high-level concepts so that you can just get on there and rapidly design and rapidly iterate on your design. So this will also translate to the STM. So it's not a black box where we put stuff in and we give you an answer. It's something you go on there and you can collaborate with all the other stakeholders and trying to understand the information. The bit that's new for us to the STC, so the Space Traffic Center, that was not part of the initial design, is the ability to assimilate data from outside. Design, you just simulate and model everything from within. Now, we have the ability to ingest data from tracking, ephemerides, all those type of things that are relevant to STM. And the goal, obviously, is to get that data and make information. For the users, so the stakeholders, I'm not going to go through that. It's pretty much everybody in the room, I think, falls in one of those categories. But the point is, again, to have this collaborative platform where we can all get on and have at least be looking at the same thing at the same time, and then hopefully understand each other. For the data itself, that's probably the crux of the problem. We've been talking about it for about 2 days now. And a lot of times, we're still probably stuck in this left-hand side, the reactive data. We have tracking. We have better and better tracking. So as you go down, you get better fidelity. But it's still reactive. It tells you what happened. It doesn't tell you what's going to happen. And we can forecast for that, and we have great physical models and all of that. But as soon as someone touches that spacecraft again, this is completely void. So we want to go to the right-hand side, the preventive column, where we can start ingesting a priori data on the systems, physical characteristics, system characteristics. And yesterday, I was actually super happy to hear Planet and Digital Globe saying that they share publicly the ephemerides, which I honestly did not know. So my engineers are not as happy because then I started texting them vehemently to say we need to put that in the tool right now. And so we have. So the ephemerides are like this super nicely gift-wrapped data, right? It's already propagated forward. It's got all the best information the operators know about the satellites, it may not always be so nicely gift wrapped, and that's okay. Any a priori data on the space assets we can ingest, we can assimilate into the toolkit, and we can model and push forward. Especially since the ephemerides provided by the operators only can come into play if you are operating the thing. All the debris, defunct satellites, rocket bodies, we obviously don't have anyone crunching those numbers. So we need to be able to better model, simulate, and forecast those behaviors. Behavior being kind of the keyword here, not just propagating data, but getting the behavior behind it. So from there, what do we do initially? Well, it's the first kind of, again, not easy, but straightforward output here is threat assessment, getting that conjunction analysis, trying to be making sure that everybody can know about it. So still, it's in our lab, it's a proof of concept, but it's on a server, it's running every day, it does all-on-all conjunction on everything we know of, grabs it from JSPOC, from Russia's GSE Vimpel, from TrueSat, which is that app that you can track satellites yourself, get all your conjunctions. I get an email with all the conjunctions that's going to come through this day, and obviously we would broadcast that to anyone that cares to know about it, so that if someone's email system is down when it shouldn't be, someone else knows and will come and tell them. And that's more like monitoring. It's nice, but beyond monitoring, we want to get to mitigation. The tool itself already will compute mitigation options through a targeting scheme for orbital dynamics to clear those threats. But of course, operators probably will want to do it slightly differently. We don't pretend to tell them what to do. The key point here is that if you start moving something, it may get in the path of something else. The way we do the mitigation, it's a recursive approach. Each time we move something, we rerun the whole thing. And typically, another conjunction popped up. And we keep doing it until everybody is clear. And that's kind of what you see all the way on the right over there. The nice green boxes means it's been mitigated. And we have an iteration counter that tells us which iteration in the process did that happen during. Of course, it gives us maneuvers and trajectories for all those objects and so on and so forth. But even if we don't design it ourselves, if the operators are willing to share the data and let us assimilate the maneuver plans, the ephemerides, then we can put that into that process. What you don't want is people doing mitigation in isolated matters, because you lose the effect on the overall system, and that's just where we lose information. We also want to take a step back. This is when stuff is already in space. We can use all that data and tweak out tools to think about what's the risk before we put more stuff in space. This is here just small proof of concept with we look at collision, risk collisions, density populations based on the parameter space. And again, it's not just for us as a black box. You go on the app today online, you can play with the knobs and you can see what happens, where to put your satellites. Insurance company can use it and they're going to charge you a higher premium if you put in the red box, and so on and so forth. Now, as you also start adding new objects, we also want to be smarter about it. And the nice thing about blending the design with STM is we have the ability to plan for very specific cases. And thinking about STM through the entire life cycle of the system, not just once into space and now figure out, okay, what happens now? So the first thing we do that's very easy is, again, go on the app, go online, upload the trajectory file, we'll run it. And by we, I mean the machine. It will give you your conjunctions, and you can act on it or not act on it, but you get that information. Don't be scared by all the red boxes. We put a stupidly large tolerance on the conjunctions. This is not going to happen. But that's what it is. You can put your trajectory file, your maneuver plan with initial conditions, and it'll do that for you. Of course, again, because initially we were a design framework, CTK itself abstracts some of that. If you say, I want to deploy or deorbit my satellite, here it's a deorbit sequence of maneuvers that's being targeted by the tool, and it applies a conjunction analysis on top of it. It'll do the same thing for the deployment. It'll just put you in your constellation slot, and it'll also tell you if there's any threats incoming. So this is where we are today. It's the beginning of a framework. We expanded what we could already do in terms of design to delve into more those STM-specific ideas. But the takeaway point is that collaboration, access anywhere, everybody on it, try to get from the data to the information. There's a lot of problems that still need to be solved, but that's where we are. And so what we're looking for most is people. Let's get people to tell us what they're interested in, just play with it, test it, give us use cases, partners for data, partners for information. Thanks.
Okay. Next up, we have Dr. Islam Hussein, who is Vice President of Space Systems at Thornton Tomasetti. He's got more than 15 years of experience in satellite guidance, navigation, and control, satellite autonomy, and SSA. And his group at Thornton Tomasetti provides both engineering and research and development solutions focusing on on-orbit satellite servicing, rendezvous and proximity operations, and single and multiple satellite swarm formation, and constellation control and management. So he's here to talk to us about that today.
Thanks, Therese. Hi, everybody. So, like Therese said, Islam Hussein from Thornton Tomasetti. This work I'm going to be talking about is done in collaboration with Han Kai and Moriba Jah here at UT Austin. As the slides clearly, you can tell that it's a UT Austin work. Han, I asked him to be here and give the presentation himself, but he said that I should take the opportunity and address the audience myself. So we're going to be revisiting a topic that Moriba started that work many years ago, almost 10 years ago, on the constrained admissible region. And there are many variations of it. A few years ago, there was the notion of a probabilistic admissible region. So I'm going to review that very quickly. And then today, we want to bring some realism to some of the way we model how to initialize an orbit given sensor data when something shows up on your radar screen all of a sudden. So I'm going to focus less on the technical side. Han covered a lot of the technical background earlier in his talk today. I'm going to focus on why this is important. Why is it important to think about credibility and our sources of information and the implications that would have. So I control this from here. All right, so this is what we got. So really, I'm going to emphasize on the background and the motivation for this work. I'm going to show you the implications as far as the PAR results are concerned, and we're going to conclude. But today's topic really revolves around two concepts that we hardly ever distinguish between. So let me define them first. This is a discussion about uncertainty. And the two notions of uncertainty that we in this particular community, until Moriba picked it up a few years ago with Manu Delande, is the distinction between aleatory and epistemic uncertainty. What are those terms if you're not familiar with the concept? So aleatory is anything that is truly random in nature, right? So your sensor noise, you can model that as a random process. Epistemic is ignorance related. Epistemic uncertainty is not that we don't know that the process is random or some of the statistical properties of a random process. Epistemic there could be, well, what is the physics generating this randomness? Okay, so we are sometimes ignorant about a physical phenomenon, not that it is truly probabilistic or random. It just we assume it is random only because it's convenient to do so. So aleatory is anything that's intrinsically truly random in nature, and epistemic is something that comes out of lack of knowledge that we, the analysts, have. Technically, one would be treated using probabilistic distributions. We're all familiar with what that is. And then the other one is what Han talked about earlier on today, is the use of the outer probability measures, right? So it's just an ability, it's a tool, a technique that allows us to process ignorance, okay? All right, so I want to say this is probably like a very important part of the work that Moriba is started, like I said. And I want to emphasize that the delineation or distinction between what is random and what is ignorance is not just a nice philosophical conversation to have. It has, on a very fundamental level, a theoretical implication, which is nice, which is important. It also has implications on us as a community and our desire to standardize knowledge or the lack of knowledge, okay? And then operational implications. Actually, this is very important. So the very good example that is Moriba showed in the paper with Delande, I think it was published last summer, is probability collision. All right. So sometimes the analyst is ignorant about where the object is. What does the analyst do? They model it to have a very large covariance. Okay. When you model it as a random process with a very large covariance, what is your PC going to be? It's going to be nil. So we've concluded that two satellites are not going to collide only because the analyst is ignorant. So somehow the analyst's ignorance tells us that these two things are not going to collide. I have no idea how those two things correlate, right? So this has important correlation. We may believe that a collision may not occur only because we're just ignorant, okay? So that is important. Now, being able to delineate between those two, what would we say in that case? What we would say is, well, we don't have enough information, and that is super important. One can argue, as Moriba does in the papers, TLEs, we've got some information, but we are ignorant about a lot. And the implications from those TLEs is not a good thing. What we usually say, anything we say based on TLEs, we have to be careful about that. So hopefully, this makes the point that delineation is not just philosophical or mathematical. It actually has some important implications, as we saw from the collision avoidance. It also has implications now on the subject of this topic and how we initialize orbits. So you get data that doesn't correlate to anything from a radar or a optical sensor. We literally, in the case of an optical sensor with a very short arc, what do we have? We literally have 2 numbers, all right? Maybe some rate data as well. So maybe 4 numbers. To determine an orbit, you need 6 numbers. So what do we do about the missing information? We just assume stuff. How do we model it? We model it with a probability density function, assuming it's random. But it's not random. Somebody put that satellite there with a purpose. There's a reason behind it. It's not random. The population of the catalog, the satellites in the catalog, they're not randomly distributed. They are very purposefully distributed, right? We have structures. When you look at the data, there are structures on why, on where those satellites are, and there's a reason behind it. But that is not a random process. So from the get-go, beyond the PC calculation, from the moment we initialize an uncertain track, the question of aleatory versus epistemic becomes very important. All right, so this is about admissible regions. And so a quick overview. I'm going to skip that. Han did that earlier on today. Is that working? All right. So this is not very reactive. There you go. Okay. All right, so what is, so the admissible region, like I said, I'm not going to go through the bullets, the story. I'm going to tell it as a story. You get, let's say, angle data only from your optical sensor, 2 numbers, maybe 4. Then from that, you want to start on a full orbit. Well, you complete the missing data usually by making some assumptions in the standard, at least, form. You make an assumption about the semi-major axis and the eccentricity, usually in terms of some sort of a distribution or a range of values. And then now you have those 6 numbers. You hypothesized a couple of them, okay? And then you create an orbit. You start on orbit, and usually it's an uncertain track. A par plus, the possibility, so that's the probability, that's the traditional way of doing it, using completely probability theory, randomness. In a par, but modeling everything as if it's random. In the par plus, we say, no, let's pause here. When it comes to the A and E guesses, we're going to actually admit that we're ignorant about that. It's not a probability density function. It's not a random process. We really, in one version, you can say I have range of values. It's possibly is a geo-orbit, and this puts limits on your A values. Well, we have guesses that these are, the eccentricities, these are circular orbits, so then, E is around, 0 or between 0 and maybe 0.1, something along those lines. And then you apply Han's theory on the OPM on the part that you're ignorant about, A and E, and then the rest is probabilistic. Okay. So what do we get? So I'm going to jump straight. So Han worked out all the math here and the simulations. So this is an angles-only example. So you get something that actually looks a lot like a par, as we know it. Except really the argument that we're making here is that it would be more representative of our true knowledge and our true ignorance. To give you a comparison, In the bottom, let me start with the bottom first. On the left-hand side is what the PAR would typically show, right? That is the admissible region. So we have an object that is somewhere in that range and range rate. We usually have two lobes because one could be, we don't have enough information to tell whether it is retrograde or prograde. But on the right-hand side, you start to see that actually there is a significant difference between, I mean, structurally they look very similar, two lobes, but then there's more structure. So when we admit that we have ignorance, we actually have much higher range of possibilities and uncertainties. It's not as nice and clean as the case. Now, why do we get the structure on the right-hand side as opposed to something that is nice and clean? We don't fully understand that, but that's, you know, we're still working on that. On the top, you see the particle cloud that was generated from a particle simulation. All right, so and then we repeated that also for a radar measurement. So we have the optical only with range, with angles and angle rates, and then for radar, it's also in the paper. You can look it up. We have radar models as well. So we worked it out for the radar case as well. All right, so these are the technical conclusions from the paper, but if there's a takeaway message is that this delineation between aleatory and epistemic is something that is not just a mathematical nicety. It actually is operationally very, very relevant, and it's important as far as creating a taxonomy of knowledge and ignorance in the community. So this could be a basis for admitting what it is that we know and admitting what it is that we don't know. And then, of course, that opens up a whole bunch of discussions regarding data, data quality, and standardization that we can go from. But that's yeah. Thanks for listening.
Thank you. Next up, we have Shiva Iyer, who's a PhD student in the Department of Aerospace Engineering here at UT Austin with the great Mariba Jah. His current research includes orbit determination, software engineering, and data fusion for problems in SSA. His master's was from UCLA, specializing in dynamics and controls, and he's going to talk about how we can use state-of-the-art machine learning to work on SSA problems.
Thank you, Therese. Good afternoon, everyone. So I'm going to be talking about an application that we made of neural networks to an age-old problem that of fitting orbits to tracking data. So I will skip the first slide. So we've heard these couple of days how for STM it's key to have transparent, predictable, and accountable access to data. Which includes a combination of tracking data sources and state vectors as well. Today we heard how just from one source, Leo Labs, we see a tremendous volume of measurements being accumulated over time. In this talk, I'd like to look into the problem of fitting orbits and trajectories to tracking data. So the goal here is to explore a way in which we can apply neural networks to this problem of orbit determination. So for the purposes of this paper, we basically use simulated data using our OrbitPy open source OD toolkit. So we basically took three objects in geo, one with a high area to mass ratio, the other were more typical of larger geo birds. We propagated them numerically using a high fidelity force model, including gravity, ocean and solid tides, solar radiation pressure, drag, although this was in geo, not really that relevant in that space, but the goal is to eventually use these for other orbital regimes, so we just included drag as well, and also sun and moon third body perturbations. And we propagated these three objects for 1 week at 60-second intervals. And for two of the objects, we incorporated station-keeping maneuvers. One was in latitude, half a degree, and the other was in longitude. Again, half a degree. This was modeled as a continuous thrust maneuver over a 15-minute period. And from the trajectories that were generated, we created azimuth angles. We added noise, normally distributed 2 arc seconds of noise per sensor, and then we added 5 arc seconds of a constant sensor bias to this data, to the angles data. And then we took this data and fed it through our neural network model, which I'll talk about next. And for the neural network, we just used Keras/TensorFlow, which is widely available, runs on CPUs, GPUs in parallel, high performance, fairly easy to use. So at first, before we fed any of the data through the neural network, the key thing was to standardize it to a zero mean and unit variance, because I've learned that neural networks don't do well when you have features or columns in which the scale of data is widely different. In this case, we have azimuth and elevation, and we have station coordinates, which are angles, and then we have time, which is on a slightly larger scale. Our outputs here are inertial positions, which are, again, of the order of the radius of the Earth and so forth. So we had to scale all the data. What I discovered is that although there was constant sensor bias added to the angles, I didn't really have to factor for that before I standardized the data. I just let the neural networks optimizer sort things out, because as part of the whole optimization process, it goes through a process of determining the weights and the biases. And so I just left it to the neural networks devices to figure that out. And in practice, that turned out to give better results. And so, as I said, the inputs were time, the station coordinates, and the angles, the noisy angles that we generated. The outputs were the satellites' inertial geocentric positions. Now, could have also included velocity. However, adding more output variables just would have required a much larger training data set. So with more time, that can also be added in this model as an output. So the training set upon which the model was trained consisted of about 9,700 samples, and the test data on which we made predictions were about 360 samples. So, and then these are the results. So when I say nominal, it's the high area to mass ratio object, which did not have any maneuvers incorporated. So this was basically a satellite drifting in geo. And so as you can see, the position errors were about 2 kilometers in the worst case. The next plot shows the same nominal trajectory, but in the radial, in-track, and cross-track directions. Again, sort of consistent with the previous plot. So about an error of about 1 kilometer in the worst case in the in-track direction. The next plot is for, it seems to be cut off, but this is for the maneuver in the east-west direction. So the maneuver was in latitude, half a degree in latitude. And so, and this result was a little surprising, because I expected more error in the position, because the maneuver was fairly significant. But for some reason, the ML algorithm seemed to recover quite well from this particular maneuver. And this is so a position error of about 2.5 kilometers. And this shows the same east-west maneuver, but in the RIC reference frame, radial, in-track, cross-track. And as you can see, the highest error appears to be in the in-track direction, about 2 kilometers, which makes sense because this was an east-west maneuver for a trajectory that was nearly eccentric and with a very low inclination to start with. So you would expect errors in the in-track direction, which it is consistent with what our intuition would tell us. The next plot is for the one with the maneuver in the north-south direction. Now, the results here are somewhat distressing. It's 60 kilometers off at the end of the 7-day propagation period. And these results were a little disappointing, given that the maneuver happened at the end of day 1. So basically, the ML algorithm had about 5 days of data, 5.5 days of data post-maneuver to work with to optimize its weights and biases, but the results are not nearly as satisfactory in the case of the latitude maneuver. And this is the same picture in the RIC reference frame. Again, it is interesting that the most error appears to be in the cross-track direction. Again, this was north-south, so you would expect the larger error to be in cross-track, and the results are somewhat consistent, but still, they are quite a bit larger than the errors in the east-west maneuver. So these are the total RMS errors for the 6-hour test period, the test data set. So yeah, again, the north-south errors were the largest in magnitude. And this is the RMS errors when I used 6 days of training data as opposed to six days and 18 hours. So you can see that the error values go up a little bit because you have much less training data in this case, so more test data. So you're making a longer-term prediction. So the errors are larger. So future work is basically going to be trying to apply this approach to real tracking data. So we at UT, in our group, we have access to Leo Labs and calibration data from Planet Labs and Maxar. So we're able to use that. So the goal is to take this approach and try to adapt it to a real tracking data situation and see what sort of results we get. And then the bigger problem would, the way I see it right now, is that of quantifying uncertainty, because so far I've assumed that we have access to truth or calibration data, and that's not always the case. So we will need some form of uncertainty quantification, but that's a whole topic in the area of ML that I haven't really explored. But it's a fruitful one, and this is sort of the way I see this little product evolving in the future. Thank you.
Okay, and last up, we are ending with another legal conversation. So George Anthony Long, we heard from already, but he's a seasoned civil and criminal defense litigator who possesses an LLM in space law. He's the founder and managing member of Legal Parallax, LLC, a legal consultancy firm, and is past co-chair of the Space Law Interest Group of the American Society of International Law. Thank you.
Thank you. Basically, artificial intelligence is great for what we call asset protection because it helps space objects, maneuver, avoid collisions, avoid collision with other objects or space debris. Fine, so it serves a purpose. But now the first thing we have to do when we look at some of the legal issues that might be associated with this, because there will be incidents where the law will come into play. One of the first things we have to do is overcome fear. There's an underlying sort of fear of machines, or machine intelligence, we should say, that exists, all right? And while we have to address that fear, it's sort of like this Geico commercial. I don't know if you've ever seen it, that if you're in a horror movie or you're really scared, you make bad decisions. That's true with law as well. When you have addressing legal issues and you're acting out of fear of something, you might not reach the best conclusion, the best result. But now the best way to address fear is understanding. And to me, as I understand it, there's artificial intelligence can be broken down into 2 basic core groups, which you might call coded software or machine learning. Coded software is what the machine is programmed to do. It doesn't exceed that programming. Machine learning, at least as I understand it, is that it allows the machine, based on its own experiences and dealings, to maybe expand a bit beyond its programming or its algorithms. So those are the 2 ways that I understand AI works. Now, to that extent, what a machine does in machine learning is sort of like a child. It collects information, it selects information from the universe of data available, it analyzes it, it makes a calculation, decisions, analysis, and moves on. And like a child, you make decisions and it builds on the decisions that you make in the future. That's how we would deal with machine learning. Now, as we put this into outer space, in the context, there's a difference to me between using AI terrestrially and using it in outer space, because I think outer space is a more perfect environment for it. Because one, there aren't humans there, really. You're not going to really have much human contact in outer space. Plus, autonomous machines, they can have their own defense systems. They can not have any, they can survive maybe incidents of high radiation, whereas people can't. And they can assist in scientific and exploration purposes without jeopardizing human life. So there's a benefit for using intelligent machines in space. But now, what's the problem with AI in space? Particularly when there's an incident that causes a collision in space, which will happen. Okay? Now, the basic problem comes with, one, the liability convention. Now, the liability convention, it has provisions for fault allocations for accidents that occur in space and absolute liability for damages caused when a space object falls to the ground. However, with respect to fault allocation in space, the liability convention states that fault liability is there only if it's due to the fault of persons for whom a state is responsible. Now that raises the question. If you have an intelligent machine that's operating, an autonomous satellite that's operating on its own, and it's making its own decision, and it causes a collision in space, is that a fault of a person? Okay, that presents a legal question. We don't know. Now, when we think of a person, we generally think of it as a human being. However, the law does recognize what we call legal persons. Okay, you got corporations and things, legal persons, or even ships. A ship can be sued, or sometimes even real property. You can have claims against real property. But for now, an intelligent machine, whether in space or on Earth, has no legal rights and no legal personhood, so you can't say it is a person. So again, we're back to the question. If there's a collision in space caused by an autonomous machine, can fault be attributed to a state? Because it's not by a person that state has control over. Which that's not an unreasonable legal issue, given that the Liability Convention was written in 1972. But here we are now. That's a question. But the real question comes about somewhat when we get into, even if you get around that issue, of how do you determine proximate cause and foreseeability. So let's just say, we'll say, okay, we can contribute a state to be at fault when it uses, or one of its spacecraft uses artificial intelligence. But now, how then do you show foreseeability and proximate cause? How do you show proximate cause? How do you show a machine made a mistake? Or even basic, let's move it back further. If it's just coded software, how do you show there was a fault in the coded software if the accident occurred in space? You're not going to be able to retrieve it. Those are the type of issues that I'm going to say the next generation of lawyers are going to be confronted with respect to AI in space. And in conclusion, the overarching issue of this, of using AI in space and autonomous learning and autonomous machines is this. Article 6 of the Outer Space Treaty obligates the state to supervise, to supervise the activities. Now, if a state allows its nationals to use autonomous machines working using AI is that abdicating your supervision imposed by Article 6? I don't know the answer to that. But that will be a legal issue that will be presented. Because how do you supervise an autonomous machine? Again, those are going to be issues for the next generation of lawyers that's going to be presented by AI in space, which is a reality that is coming. Thank you.
I'm going to take the prerogative of being the moderator to ask some questions on my own for a bit, and I'll leave 15 to 20 minutes for questions from the audience at the end. So definitely want to go more into talking about these systems being a potential black box. So first, Edward, I wanted to get your perspective of someone who's used this digital CA system. What were the major obstacles that you saw in data integration, and what sort of fidelity did you have as the end user of the SSA data? What did you see in terms of inputs, or is it sort of a black box system? What was your experience as a user of the data?
Okay, thanks for the question. So I'm not the implementer for the integration between NeoLabs and Digital Globe, but as a Leo Lab API user, it's very easy. I mean, you can write some scripts, you can do CURL, they're very easy to use, and you have access directly to their measurements and covariance, Dopplers, instrument bias, and all kinds of stuff. So.
Okay, that's
not
certainly good to hear.
Yeah.
And Loic, as someone who's designing a system that's integrating different data sources, how do you plan on evaluating the accuracy of data provided by sources as you incorporate more sources? And do you have any concerns with being too inclusive of data sources and potential corruptibility of data using sources that are either unintentionally or intentionally very inaccurate?
I mean, so it's a lot of questions, and so mostly they're hard questions, and I don't actually have honestly complete answers for them. And some of it I'll just push on some other people in a way. The problem with inclusivity, I think, is, I am not concerned about it myself in the sense that the more data we have, I think the easier, or at least the more obvious it is to get to a consensus. If it's intentionally or unintentionally inaccurate, then that's more complicated. Mostly it dwells into things like warfare at this point, and that's much beyond the scope of honestly a thing I've had the chance to really think about it at the moment. I think the unintentional inaccuracy would get curated through the reconciliation process, the data fusion. People doing work with like Slingshot on this will be confronted with that problem as well. On our end, we're hoping that by the time it gets to us, this type of data, more intrinsic data issues will have already been somewhat mitigated. Then on the first part of the question on so how to verify accuracy, I think it's even a bigger question, and it goes exactly to what Islam was talking about. I was just talking about it with Moriba over lunch too, is the first thing is to know what we know and to know what we don't know. And more than inaccurate things, the more concerning part is not knowing what we actually know. Once we know, and we know it's inaccurate, or even if we know that it may or may not be accurate, that's different. But first knowing that we actually know it is there. It sounds like a lot of gibberish, but essentially then you apply their theory to it. And if you can distinguish the things that are, like Islam mentioned, systematic errors or keeps on popping in a predictive way, then you know that you're missing something, and that's okay. Then if you can, stem out the things that you don't understand what's going on, that's I think the first step.
Thanks. I wanted to talk more about knowing what we don't know. So for our simulators, Islam and Shiva, what are the biggest conflicts that you've seen in data interpretation across stakeholders, and what do you think that might mean for data fusion? Because it's one thing, you're both doing great work in characterizing uncertainty, but unless we have people implementing that, it doesn't do us a lot of good.
Defer to you on that.
So I might answer just a slightly different question, but I look at what we're doing here as trying to just be honest about the fact that there's a lot we don't know. I look at a lot of the work done, the work that Loic does and Shiva is trying to, we're cleaning up, right? We need to be, sometimes the data is very clean and crisp, but for whatever reason, we don't have complete metadata, for example, right? For whatever reason. So basically, really, I look at what I'm doing, or at least what we talked about today, as trying to understand standards. What's the quality here? And with the lack of quality, once that is established, well, what can we do with it still? I mean, the really good example is like the TLE example again. We just attach a covariance to it, and some people do, and that's not necessarily the best thing. So let's just admit that we're ignorant about it. So.
In my own experience, I totally second what Islam said. As part of another paper that was presented today by Jason Stosh in the morning, so there was another approach we explored for the same paper, where we applied the classic Kalman filter technique and tried to fit TLEs and data and state vectors from a couple of different sources, Numerica and ULabs. But the results weren't great. In fact, the fused results were worse off than the underlying data. And part of it was because, given the constraints of time and all that, we used stock uncertainties and stock generic covariances while we were fusing the data together, and that gave results that were worse off than the original data sources. So I don't know how to get around that yet, especially, again, as Islam said, when you have a source like the TLEs that don't come with any uncertainties. So you're left with again, ad hoc schemes to ascribe uncertainty to those sources. So.
Okay, I wanted to move on to a more legal question. When talking about AI and machine learning algorithms, there seems to be, in general, a lack of legal precedent in assigning liability to them, not just in space. There's definitely concern about this. It's already been raised in the healthcare field with something called black box medicine. So one case that I saw, a vendor made unsafe cancer treatment recommendations because the AI was trained on synthetic data and not real data. Europe has gone as far as to require that decisions of AI examining personal data be explainable. Is it possible that we'll see some sort of legal precedent on AI and machine learning in other areas that we can then apply to space? And what areas do you think we should be following for our legal experts?
I think one of the areas where it may come applicable in space, at least with space objects, is the issue that's being litigated now on driverless cars. I think that may begin to set some base work, some foundation of law, all right, from which you can then extrapolate to its going into space. For instance, I live in Arizona, and of course, Arizona is one of the test states for the driverless cars, and there have been some incidents, some fatal with the driverless car. And then again, that also begins to raise up the issue of essentially liability. Is it a programming issue? Is there some fault in the machine? I'm not sure how those issues will be worked out judicially, but that will begin to set the parameters, or at least a foundation that can then be extrapolated perhaps into space.
I think also one of the things that I've heard my colleagues addressing is this quest for some level of precision. And the problem is, and I believe you used the word aleatory. Aleatory comes from the Latin word for rolling the dice. If you've ever played craps, you know how logical that is. And so as a result, because fundamentally we're dealing with human values, we're creating the artificial intelligence to react in a particular way to a particular type of situation. I have a car that tells me you're going too fast for the car that's in front of you, and it will apply the brakes, whether I like it or not. And this leads immediately to the question that has to be answered by all of you, or each of you. Is your car smarter than you are? And if the answer to that is even marginally yes, then there is an ethical issue there, because there is the human factor that is being overridden by the mechanical factor. And the technology has to account for human beings, or else, and this is the problem, the first law problem that I alluded to. What if we develop a machine that is capable of such a level of independent thought that it decides that we are not tidy enough, and it sets out to destroy humanity? That's not science fiction, folks. 50 years ago, Buck Rogers was science fiction. It's not now. 50 years from now, what will that robot be capable of thinking? And do we know what it's thinking? And that's a problem.
Right. And if I can just follow up, I agree, because I basically think that in the future what we're going to have are two types of intelligence that exist. We're going to have human intelligence and you're going to have machine intelligence. And is there a way to integrate them or to make them coincide, maybe within a legal framework or not? Because a machine cannot have functional same intelligence as humans, because we have a lot of aspects that come into play: emotions, biasness, and a lot of that will be absent from machines. So how can these two intelligence coexist? I think maybe.
Well, and at its root, and I think you'd agree with this, at its root, the question is who, and this goes back to my point about the pen, who's in control? Because if the machine is in control, finding liability and legally gets really bizarro. Mm-hmm. Who was the programmer? Who was the manufacturer? And this is what Tesla, by the way, is wrestling with now, with these fatality accidents that they've had. Who's liable? Elon Musk? It's the only deep pocket they've got. But who dreamed up the program? And then in the AI world, whose ethical standards are going to be, and existential standards are going to be applied to fabricate this scenario for the machine to respond?
So that leads to my next question, which you set me up perfectly for. So in thinking about ethics in AI, this is for all the panelists, different cultures could have different frameworks under which AI could be programmed. For instance, one country might prioritize its own assets in the region over those of all other countries, or you could have operators playing a game of chicken, trying to figure out if the other operator will move if their asset's more expensive. So how do we ensure international cooperation in AI standards in the STM domain? What do you think the next steps are?
52 pickup. I rather seriously doubt that you will, except at a most basic level of on or off, achieve much international standardization.
It's a timely question because EU actually just released their AI guideline, their white paper yesterday, so you should check it out if you haven't. But from my personal opinion, we should focus on three things. Like, we should focus on the data sets and how do we generate them, and kind of like a record keeping, and have human oversight on it, as simple as that. From an STM or SSA domain perspective, I feel like we just don't have enough data yet. So that's like my perspective.
And I'm going to go back a little bit to the previous topic again. So on the technical side, on the research and development side, a lot of the work that's happening actually by the U.S. Air Force, for example, is not just developing autonomy for the sake of autonomy. It's actually mostly about establishing trust in autonomy. So there were several events over the last few months that focused particularly on how much, and this is not a philosophical question, it's actually a very technical question. How do we, going back to a question you raised, how do we assure that no matter the level of autonomy we give a space vehicle, we want to make sure that it can protect itself and, of course, protect others. So on the technical community, we spend a lot of time thinking about that.
And I think part of the answer to her question is when you get into the issue of human oversight, that's where cultural differences of the observer are going to play into how you structure the data.
Correct, and that would also can cause problems because if you just put data into a machine and let's say that's how it makes its decision and you don't take into consideration maybe the human biasness that gives rise to this data because then a machine can make a decision that, well, if a person lives in this zip code, then, the tendencies are X, Y, and Z. And, that can be because of maybe human biasness that has, is the source of that data. And as I understand from one of the aspects of AI now is how do you sort of balance out, our programming and dealing with algorithms to machines to sort of move out those sort of aspects. Because I've heard California is considering using AI to make parole decisions. And, if you put in data, just go strictly data, a machine will come out that, well, if a person is of a certain ethnicity, they're most likely going to come back to jail, so maybe they shouldn't be given parole. Okay? I mean, that's just basic on pure data. So those are some of the issues.
And these folks may not be as aware as you and I are about the phrase mechanical jurisprudence, which is exactly what you're talking about. You put the facts in here, the law in here, and you push a button and it spits out a judgment.
Right.
You immediately remove the human factor, at which point, speaking as a senior district judge, I become completely irrelevant. I don't like that. But the fact is that when you start putting together an array of data, if you're expecting that to be the basis for some sort of decision, then there has to be a human factor taken into account as to the source of the observer.
Right.
Because I think it's safe to say that a tribesman from the Amazon is going to have a very different worldview from someone even in California. I do have a bias.
You're correct, because I would say this, just that the federal government did do an experiment like that with the sentencing guidelines at one time. They were mandatory. You could not deviate. But then, actually, once it got to white-collar crime, they decided judges needed to have that discretion. All right, so now, that human decision factor comes into play as opposed to, mechanical jurisprudence.
Well, that's the headline for today, Roger Stone.
Exactly.
Complicated issues that we're not really resolving, and that's okay, I think. But to your initial question as well is, if we expect that different humans will have different worldviews and hence different decision-making processes, at least one way to approach it is to make sure everybody gets to have a seat at the table into the making of the machines, so that then the outcome can be at least a reflection as varied of a human spectrum as possible.
And that would be the ideal, of course.
We tried a couple of years ago, we had some funding to look at, if somebody does maneuver a satellite, whether it's an AI or a person, well, how much of the culture impacts that decision? Is it a fault? Is it malicious, or is it just because the person running it is I come from Egypt, and I know how the space agency over there is like. They could do a lot better. So faults coming out of that particular office may not be very trustworthy, but we shouldn't go off and just assume malicious access. So there are cultural impacts that can also be analyzed, and you can look at that kind of thing. Yep.
So I had a question along that line. So we've been talking about better algorithms, fusion of data sources, and just understanding better where the data comes from as a big step toward STM. And mentioning all these different cultural issues, are there any additional parameters that our quantitative models should incorporate in the future, which aren't incorporated today by these decision makers who look at probability of collision, and what should they consider? I mean, I know qualitatively people talk about asset value, density of the assets in the region, decrease in operational lifetimes by making a maneuver, but what do you see as being the next things that we need to incorporate in our simulations?
I think some people have alluded to that maybe yesterday, whereas maybe a better metric than probability of collision or the other independent metric is the risk is really the probability of collision times the consequence. I think we do a lot of work towards is there a threat and how to deal with it. We don't necessarily do as much work to see what happens if we don't get to mitigate that threat, or if it happens. Then we have, is it a giant cloud of small debris we add to the population? And if we could maybe understand that posterior part better to compound the effect of the probability of collision, maybe that help us make different decisions.
And also, I think, the old adage, with great power comes great responsibility. So, without naming names, the number of mega constellations we've heard many times over the last couple of days rapidly growing. The constellations are getting bigger in size, and there are more and more of them. So one would think that operators of these constellations, with all their increased power and reach and all that, their responsibilities are correspondingly greater. Although that being said, I don't know how that translates to regulations or laws or policies to kind of limit, what they can and cannot do in space. So it's way beyond my ken.
Well, I hate to say it, but the reality is that sooner or later, no matter how precise the constructs you create, whether or not it's going to be implemented is going to be a political struggle. And it may be a geopolitical issue. And speaking as one who's survived a lot of elections, it's not a tidy business. And so in the process of creating what you are creating, you need to consider that not only do your cultural values come into play, but who you're pitching it to. Because finding agreement, I'd say if you took a random sample of 5 people here and asked them what time it was, you'd get 7 different answers.
Okay, I have one more legal question before I open up audience questions. So currently there's no legal precedent in assigning liability for on-orbit collisions. So if we can't even assign liability without AI and machine learning, do we have any hope of assigning liability with AI or machine learning algorithms? Do you think there's an instance where it might actually be easier to prove fault with AI and machine learning than decisions of human actors? And what do you see as the next steps in a liability determining legal regime with or without AI and machine learning?
From a technical perspective, if machines can do things better than humans, and I do believe they can, well, if we have any hope, we probably have to rely on machines.
I think that a lot of that would depend upon the skill of the programmers and the people who launched it as to their mathematical skills, and then does either of the vehicles have software aboard that enables it to avoid the collision? I mean, if a Mercedes can do it, they ought to be able to do it up there.
Correct. I'm thinking eventually may go to what we like in the airline industry, they have what they call the black box that collects everything. Whether there's something that's eventually done with that in space to an extent, where data is always being streamed to some other location to be maintained in the event of that, I don't know the solution, but there has to be a way of maybe preserving or accessing some data that actually reflect, to show what caused it or what happened. And how that's done, I have absolutely no idea.
Sue the manufacturer.
And I think, we will probably at a point soon where autonomous systems in turn spawn off an entire generation of autonomous systems and then off to infinity. So at that point, how do you trace back any fault or liability to its original human creator if systems are just spawning one another?
Well, the lifespan of a lot of these items that are in Earth orbit is relatively short. And as you say, let's say that the lifespan of a couple of these is 10 years, and they crash into each other, and there's no recent data coming from them to give us a clue as to what went wrong, except the laws of physics, and that's not very helpful in court.
That's why we're not
Where it's been tried.
Okay, on that note, I'd like to open it up. Mariba's got a question already.
I'll try to whittle down my multitude of questions to the following. So, heard about facts and machines being able to just take facts and make conclusions, that sort of stuff. So, I guess my question to the panel in general is it naive to kind of assume that the facts represent truth versus something that may be truth? In other words, is there any sensor that measures truth? And so given the presence of biases, I mean, even the way you collect data, even the manner in which you collect it, how you feed it to different algorithms or to people or whatever, these things, by and large, have confirmation bias built into them. So how does AI and ML get around the fact that truth is never known? Decisions are never made on truth. Answer me! Go ahead.
Well, a great judge, Pontius Pilate, once said, "What is truth?" And that actually sets the stage for the 21st century for anybody under the age of 35. And they say, just as you did, there is no absolute truth. And if that's where you're starting from, then AI is in trouble from the threshold.
I still can't get beyond Pontius Pilate.
But you're right. Truth is, a lot of times, is a product of perspective to an extent, which raises the issue that if you can remove all of our human attributes, our human biases, our human perspectives from an issue, is that more the truth? You know, as how a machine evaluates things without all this human emotional input, is that closer to the truth? I don't know.
The closest thing I can think of from the technical perspective to what you're raising is, so in supervised learning, right now we assume that here's the data, and that's the label, so everything is nicely labeled and crisp and clean, so there's a lot of work going on right now on certain data. The data that goes into the machine learning algorithm themselves are fuzzy and it's not just if X then Y, it's if X maybe Y, right? So I think that's like the closest thing I can think of, for, and then unsupervised learning, on the other hand, it makes its own truths, right? You just provided the data, it looks at structures and tries to identify its own truths, I guess, that it uses later on for some decision making.
Right, and at least as far as my current work is concerned, for me, good enough truth is good enough for me to work with for right now. If I can get the conference paper out and keep my exactly. So.
But that's probably more to reality. Enduring. That's probably more.
Wait, we got a mic behind you.
That's probably more enduring over time than anything else we're talking about.
I am a practical guy.
Is the whole human experience has been what's good enough? What's good enough? Because at some point, you can't move forward unless you make a decision, and the analysis by paralysis or paralysis by analysis. So you have to make a decision, and it's got So I've got these sets of options to make a decision against, and hopefully I make the best one. Unless you're my 15-year-old son, and then that all bets are off. So.
Well, going to what George said a few moments ago, judges are given a whole pile of statutes and previous cases that provide guidance. But there comes a day and in fact, there are several judges who will confess this, about 90 days after you take office, the book of rules runs out. And from there, for however long your career lasts, you are essentially in a day-to-day world with a constantly changing set of facts that are presented to you. And so what happens today and the judgment that you make today is perhaps not one that you'll make 5 years from now on similar facts, because maybe societal values have changed. Maybe you have had some kind of personally shattering experience that changes your perspective. And this is the human problem that unfortunately a lot of technology simply cannot grasp, because the technology, I don't care how good we are at creating it, we cannot make it care. And we cannot make it know. It can learn, but it can't care. My car doesn't really give a damn whether I hit the next car or not. It just tells me don't do that.
Okay, Mark had a question?
Yeah, this is for Islam. So when I was an undergraduate, we took an error analysis thing. We used Bevington. And he talks about two kinds of errors, random and systematic. He didn't use the fancy terms you used, which I can't remember. But can you help me understand if, I mean, random sounds like the ones you were talking about, the first one, which is random, but systematic, the way I understand it, I didn't understand from your definition if that's of things we don't know, if that's the same as the systematic error. I'd like to know if there's a one-to-one mapping, or if there is a fuzzier mapping between those two.
This is it.
Stuff that you presumably could learn away. Eventually with enough information, you could learn it away.
Mike, brother. No, just yelling at him.
Thank you. H.R. Zucker again. I once heard a phrase, facts are negotiable, but perception is not. So with that context, if you had the ideal experiment, what would you like to do that would have a universal language that it means the same thing to each one of you, from space object identification or traffic management perspective? You know, I once heard math is the purest of language. It's a universal language. So from that context, any thoughts and observation?
I'd have to say that the attempt to create such a universal language is something towards which a lot of people have spent a lot of time. But when you're dealing with human beings, the very variety of the subject is going to slow you down. And you're not going to have universality. You're going to have variations. And I know that I'm preaching heresy to this group. Accept and embrace the chaos, because that's what you're really dealing with.
Islam, you look.
Well, so my first thought is we look to someone like Diane, people who are going to be establishing systems that we're going to use on a day-to-day basis. On the technical side, the best we can do as a community is iterate and work on trying to figure out what is the finest taxonomy for our knowledge or lack thereof that we can come up with. But we need to keep an open mind, because if we don't have an open mind, then practices of old are going to stay with us too long, and so as long as we keep an open mind and iterate on the technical side to provide the actual operators a framework that is inclusive and healthy.
I think Brad had a question.
I'm struck by a theme that's kind of come out on this panel. It's really amazing to see the juxtaposition of someone who's just kind of come into the arena and said, I think there needs to be more data, and you're spot on. That we agree from a number of different angles. We have a career researcher who said, we are assessing what we don't know and finding more advanced ways to quantify the fact that we are information insufficient, right? And yet we're doing AI training on TLEs, which are based on data that are undersampled for a different set of requirements that do not meet the requirements of space traffic management. So I am terrified by the concept that we're going to train autonomous algorithms on data sets that are insufficiently sampled in the first place. And so I'd like the data scientists in the room and the folks that were talking about AI to discuss what the actual data levels might need to be, and they should be oversampled. And this is not a requirement we're flowing up to leadership right now in terms of what we need to invest in this, but we are not observing these things often enough to do the kinds of things that everyone on this stage are talking about.
Right. I mean, I balk at using something like TLEs to do machine learning and AI. Yeah, that's crazy. However, there is value in some of that data. So a TLE provides you with something, but the point here is to be able to know what that something is and what it's not, and get the most out of it, right? But then, we look to people like EXO and Leo Labs to provide us. This is why we're having this exercise with what you guys have been doing over the last few years, what I used to do over the last few years.
Perhaps a practical approach, an attempt at a real-world approach might have some value in certain of these areas. And I'm thinking of the self-driving cars. And you take a self-driving car and you put it on the road from San Antonio to El Paso at 80 miles an hour. Statistically, you're highly likely to hit a thunderstorm. Okay, lightning doesn't have to strike the car for it to be fried. It goes off the road at 80 miles an hour and kills somebody. Well, how self-driving do we really want that car? Don't we want to have somebody with their hands on a steering wheel as a backup, if nothing else, to the machine? That's a practical question. And obviously somebody, I hope, has designed the car so that it won't be affected by a nearby lightning strike. But it could happen. And going into design things and data and so forth and so on, who do you want to serve? Do you want to serve the machine and the machine system, or do you want the machine system to serve human beings? And once you've answered that question, then you can go forward with whatever you design.
Whether we're talking the modern, machine learning-based methods or just a human decision process in general, I think the general theme has been it's all about the size of your training set and have you seen the data that underlies the types of conclusions you want to derive from it. And we simply haven't seen enough of these cases because the data is too sparse. And so, anyway, I think that's a kind of a unifying message that I'm hearing from everybody is, we've got a lot of work to do, but it's just starved for the actual information that we need to be able to do this.
Okay, but imagine my job as a judge when you're bringing data to me after I've been to this conference. What level of precision am I going to expect from the data that you bring before I have to make a decision?
If I'm reading between the lines, so the concern is about using machine learning for things like orbit determination. That I actually don't think is as maneuver planning, yeah, right. This is where I see less of a role for machine learning and AI than it is in other places like actual autonomy for a satellite. This is where that would be more applicable, but at best, what some of the work that I've seen using machine learning for propagation of uncertainty or just do uncertainty propagation, it's mostly about identifying the parameters of the sensor process, right? really, that's the only value I can see. I don't see anything.
I mean, and also to some extent try to make sense of all the volumes of data that is now available. What Edward mentioned before, just from Leo Labs, you have this tremendous volume of data. It's just not humanly possible for most people to sit there and try to make sense of it in any reasonable amount of time. So the next best thing is, you try to train some algorithms and, hope that they do a reasonably good job in a reasonable amount of time. Absolutely.
Well, now you're going into the big data discussion.
But I think what we're talking about is trial and error, basically.
So one more
Liven
question.
up.
Yeah.
Question in the back, and then comment from Diane. Okay.
I have a very quick comment. This is Diane. And I'm offering this as a person who's a lawyer, but I also speak SSA and STM. I think something that might help the two jurists up there on the panel would be to understand what the AI that is being discussed in this forum is being used for. So it's not being used to drive a car or move the car per se, not at this point. It's being used to inform decisions that could be made. So it's like a decision aid. So it's culling through a whole lot of data, and it's showing anomalies and things, but there's a human in the loop at this point. So I hope that helps clarify a little bit. Thank you.
I understand, but one of the aspects that I was looking at is when we get to the point where the humans are not in the loop. And I'm thinking that that's where AI has a benefit in space, is that you can begin to remove the humans out of the loop and have the machines operate autonomously. That's what I'm saying.
Yeah.
It's a next generational issue of lawyers. But it's all we're doing, again, if we're looking at, what data or the choices that the machines are giving us, then the question becomes, as a human, do you limit yourself to what this machine is saying, or do you go beyond that machine? Or what is your obligation to look beyond what that machine is telling you?
So I think we may have time for one more question.
Yeah, just I want to disappoint a little bit everybody here with the amount of data. You have to understand that artificial intelligence, especially deep learning, is moving away from working on a lot of data. Simply because human being and human intelligence doesn't work on iterating and try to do deep learning for millions and millions of iterations. We learn on few examples, okay? Indeed, one of the hot topics of deep learning is meta-learning, where we learn to learn, and the application, as well as the idea that only with few shots of data, but trained on a distribution of data, you will achieve same performances, okay? Now, I do understand that more data is better, but keep in mind that the artificial intelligence community is moving toward really implementing a cognitive system that learns with few data. I think we have to catch up as a community at SSA to this kind of approach, okay? I think this is extremely important because it's one of the hottest topics in AI nowadays, okay? The other things I want to keep in mind is that we are modelers here, at least a lot of people here, right? And we work with equations. We have models at hand that can generate data. Another thing that us as a community in SSA, we are not exploring is this idea of transfer learning. We have at hand simulators that can generate a lot of data, and then the question is that can we transfer to small amount of data that are, as Brian said, are undersampled. This is another area that we need to explore. Another thing I want to mention is also that the reasoning that machine learning is doing in terms of trust, trusting and achieving the truth, every decision works probabilistically. Even if you have nice data, nevertheless, when, for example, a system does classification, it always gives you a probability of classification. That's the confidence that you have about your answer. And this is something that needs to be taken into account eventually when take the answer of the machine as a face value. Okay? So.
Okay.
Actually, to maybe excuse me, clarify one thing, I think it echoes to what you were saying. At least when I use the term more data, we need more data, I don't necessarily mean in volume. I mean in the quality and in the intrinsic kind of nature of the data. I agree that the TLE is very little data. That's what I would mean by more data would be something that describes whatever it is you're observing much better. If it's a state vector, it's an ephemerid, it's attached to a whole set of ancillary data with shape, drag, ballistic, all those things is what I would mean by more data. It's, again, it's not about the volume, it's about the quantity. And now it goes to your question is, or question, comment. At this point, if you can better, if data point is so much richer, of course we don't need really many. I think sometimes we go to the proxies that since we don't know hardly anything at each time, let's just know a lot of other times and hope to fit something through it. But we miss a whole lot of the physics in the process.
So also, the question that I think you're heading towards is, are we teaching these machines to learn as we learn, or are we letting the machine go?
Okay, Mariba's giving us the hook, but I think that is a great question to end on. So thank you, everyone.
I didn't mean to be a finish.